Welcome you all to this session on digital communication. Now, as you know that in today's world, or rather in today's communicative world, digital communication is the most hot topic, or it is the most important topic. Today we are discussing about digital communication. For digital communication to occur, we must know at first the sampling theorem. That is, as you know, that in today's world also, we have used only the analog signal. In today's life, we always use analog signal. In a very few cases, we actually having the digital signal in our daily life. So in today's world, whenever in everywhere we are using analog signal, but as we are talking about digital communication, so the first step or the initial step should be to convert that analog signal, that is the universally used signal. Once we want to use the digital communication, we must transfer or transform this analog signal to a digital one. So the first step is to conversion of the analog signal to the digital one. And for that reason, we must know how the analog signal can be digitized. And sampling theorem is the initial part, or it is rather useful for this to happen or this to occur. So to convert one analog signal into a digital signal or into a digital one, we must know about the sampling theorem and the sampling rate. Let's discuss about the sampling theorem. Now, as we know that this is this is an analog signal. Now we want to convert this analog signal into its digital form. So let us uh, let us consider that as we know that for a digital signal we have precise values, that is we must have some definite values, some finite values, whereas for an analog signal, the values are discrete in nature. That is, they are, or for analog signals, the values are continuous. That is, the signal starts from some value, say it is 2 volts, then 2, and the maximum, and then returns to 2 volts, and then after it goes beyond 2, that is less than 2, and then it repeats itself. But for when this signal is converted into its digital form, the digital signal may contain, or the digital signal must contain, some discrete values, that is some discontinuous values. Now, how to get some discontinuous values or some discrete values from this analog one? For this to happen, let's sample these signals. Let's sample this signal into these different points, into these different points. So this is the time and this is the amplitude part. Now I have sampled these frequencies. What is the meaning of sampled? Sampling means I have take some definite values at some definite or at some defined time interval. Let's, for an example, I have taken that after 10 seconds, I will observe the values of the analog signal, or for this signal. I take a pen and a paper and I am going to note down the definite values of this signal after each 10 seconds of interval. And then I have, or I may found these particular points or these particular values after 10 precise seconds of interval. Now, if these values are taken, and if I draw, so after 10 seconds, or taking the values after 10 seconds of interval, these are the values I obtain. Okay? So these are the discrete values from the analog signal I have recorded, or after sampling, I can find these particular values over the time interval. Now, if the original signal is going to be reconstructed from these different values, what will happen? I can draw or join these different points, and let's see what I found. So this is the signal which I can reconstruct, or which I obtain from this analog signal, or from after the digitization or after the sampling of this particular signal, I obtain this type of signal. Now, if you consider this is the original signal, or this is the signal actually which I have obtained after sampling, if you consider, you may consider that this is the original information or original signal, or it is the replica one. No, this is not the replica, as because this signal and this signal differs about some amplitude, some values in the amplitude. Now, if the signal or if the information lies in the amplitude of this signal, then we missed it. We actually missed the peak and the bottom of the signal. As you can find that there is no information here, and also I have missed this information from this part of the signal. So if the information lies in the amplitude of the original signal, then from after the conversion, or after using the sampling, after sampled the signal, we actually missed some part of the information from the analog signal. And as you know, that missing information is a very bad, or is nothing communicated, nothing linked to the digital communication. So communication means you must communicate the whole information, that is the entire information, from one point to other. So if after some technological advancement, or after some application of technology, you are going to miss some of the information originally resides in the signal itself, you actually do nothing. So how can you, or how can we overcome this type of misbehavior, or this type of rather, how can we overcome this type of problem? How can we communicate, or how can we convert an analog signal into a digital one? Obviously, the step is this only, that is, you must digitize the signal by applying this sampling theorem. Now, the theorem, as I talk about the theorem, that is the sampling theorem. So what is the sampling theorem, or what is the statement of the sampling theorem? We must know what is the sampling theorem, otherwise we can't apply this theorem to get a digitized signal from the analog one. And according to this theorem, what it states? It states actually that a continuous signal can be reconstructed in full a continuous signal can be reconstructed in full or properly sampled so this is not the case for a proper sampling. So a continuous signal can be reconstructed in full or properly sampled only if it does not contain frequency component above one half of the sampling rate. Again, I repeat that a continuous signal can be reconstructed entirely or in full, properly sampled only if it does not contain frequency component above one half of the sampling rate. Now let's take an example. So a sampling rate of 3000 samples per second, a sampling rate of 3000 samples per second requires the analog signal to be composed of frequencies below 1500 cycles per second. Now let's show this again in the figure. Now, if I take the sample rate or the time interval close enough, if I take the sampling time interval close enough, what will happen? If I take half the time interval, that is after each 5 seconds, I sample or I have taken the values from this signal. So what will happen? So here the values can be plotted as this. I have taken values from the analog signal after each 5 seconds. So previously I have taken the values after 10 seconds of interval. Now I have taken the values after 5 seconds. So these are the values which I get from the original signal by sampling the signal or by taking the discrete values from the signal after each 5 seconds of interval. Now, if I want to reconstruct this signal, see the original one can be drawn or the original signal is obtained. So this is the proper way of sampling. I think you get my point. So this is the proper way of sampling. So here lies a limit. Here lies a limit, that is, what will be the time interval of taking definite or of taking different sample values. Okay, so the question lies here that what is the rate or what is the minimum rate of sampling, or in other words, what should be the minimum time interval to reconstruct, to take the definite values or to take the discrete values from the signal itself. However, to get the original signal reconstructed at the receiving end or at the transmitting end. So you want to, or we want to rather reconstruct an analog signal. We can't bother to leave some information part from the signal. So what will be the limit, or what will be the time interval, or what will be the minimum rate of sampling? It should be mentioned, or it should be known earlier without applying the sampling theorem. Okay, have you any doubts about this? Please mention. Just mention in the comments box. Is it clear till now? Requirement of sampling. So let's answer Shubhajit's question. So what is the requirement of sampling? I have told earlier that requirement of sampling actually the first and foremost condition or uh, first and foremost purpose of sampling is to convert an analog signal into its digital form. Forget about any type of communication now. Just remember that we want to convert an analog signal into its digital counterpart. So here sampling is required. So sampling is required to convert an analog signal into its digital form, nothing excess. Okay? Is it okay, Shubhajit? Okay, fine. So let's proceed further. So now we come to this point that we already informed or we already know the fact that sampling is required to convert an analog signal into its digital counterpart or into a digital form. As because without converting an analog signal into its digital form or without converting an analog signal into a digital signal, you cannot proceed in digital communication. Fine. So this is the way we can sample an analog signal into its digital form, or we can convert an analog signal into its digital form. Now here I am questioning about, or I have already inquired about, that there must lie a limit. There must be a limit of sampling frequency. Say we have a signal which is around 1 kilohertz frequency, or it is a baseband signal of 1 kilohertz frequency. Now what will be, I want to convert it into its digital form, or I want to apply this sampling theorem. Now what will be our sampling frequency? Now for this to happen, Nyquist has given us a rate of sampling. Nyquist told us that the sampling frequency should be greater than or equals to the frequency of the original signal. So if a 1 kilohertz frequency signal is to convert it, or if a 1 kilohertz signal is to be converted into its digital form, according to Nyquist theorem, or according to this sampling theorem, sampling frequency should be minimum 2 kilohertz frequency, that is twice the frequency of the original signal. That should be the sampling frequency. Okay, so you have to sample this signal minimum twice the frequency of the original analog signal. Okay, now so I have already shown here that if the sampling frequency is less than that cutoff or that Nyquist rate, what will happen? Or Now, if you are you exceeded the values of the sampling frequency. That is, you may talk about that, no, sir, I am going to sample my signal about thrice the frequency of the original signal. You may proceed in this way. Now, if you apply or if you sample the frequency thrice the frequency of the original signal, what will happen? You may find some extra values, some additional values from the signal, some additional values, some additional discrete values from the signal. I don't think, or rather you may don't think, that this will help you further to reconstruct the original signal, as because this is quite similar to the original signal. Now, if you go beyond that sampling rate, or if you have exceeded the sampling frequency about thrice or fourth or fifth as you wish, then you may consider some additional values as well, but this will not help you to reconstruct the signal in any way. So that will give you some redundancy, some additional values, and it will cost, and it will not be some cost effective. So it will be a costly affair. So as we can see that whenever we want to, or whenever we have to convert an analog signal into a digital one, into a digital signal, just obey or just maintain the sampling rate told by, or as shown by Nyquist theorem or Nyquist rate. Okay. Now, till this part, we have used two different terms. Two most important terms are already discussed. One is the Nyquist frequency. One is the Nyquist frequency. Nyquist frequency. And the other one important term, that is Nyquist rate. So these are the terms which I have already discussed while discussing the sampling theorem. These are the terms, that is Nyquist rate and Nyquist frequency. Now the Nyquist frequency is actually twice the highest frequency present in the signal. The Nyquist frequency is twice the highest frequency present in the original signal, that is the Nyquist frequency. Okay. Now what is the Nyquist rate? And Nyquist rate is the minimum sampling rate. So Nyquist rate is the minimum sampling rate, which is actually equal to 1/2 of the sampling rate. It is the minimum sampling rate, as because what I have told earlier, that according to sampling theorem or according to Nyquist frequency, the frequency of sampling should be greater than, or at minimum it should be equal to twice the frequency present, or twice the maximum frequency present in the signal. So if twice the frequency is the Nyquist frequency, then half the rate, half will be the rate, or half is the minimum sampling rate. So Nyquist rate is the minimum sampling rate, which is equal to 1/2 of the sampling rate, as because rate and frequency are inverse to each other. Okay. Is it clear? What is sampling frequency? What is Nyquist criteria? Or what is Nyquist frequency and Nyquist rate? Actually, sampling theorem in many books, sampling theorem is also considered as Nyquist theorem also. So, is it clear to you what is Nyquist rate and what is Nyquist frequency? I'm waiting just. Okay. So let's move on to this theorem more vividly. That is, let's take a more detailed analysis of sampling. Okay. So let's take an unsampled, or rather an original signal in its time domain. So let it be the unsampled or the original signal. So this is the unsampled signal. It is shown in its time domain. Now, if let's draw its frequency domain. Now, it is actually its frequency domain so here the amplitude is plotted against frequency axis. So let it be figure A, let it be figure B. So figure A shows an analog signal and its frequency spectrum is actually shown in figure B. Now let's take a case that I have applied the sampling theorem. I have applied the sampling theorem and actually the irregular shape of the wave may missing here, or you may find that the original signals, that is unsampled signal, and this signal is quite different, but I've tried to draw. Let's take the sampling frequency is greater than the Nyquist frequency. That is, I have sampled this around 3f. Now, this should be the sampled values. So these are the sampled values, which is sampled at thrice the frequency of the original signal. So this is actually the original signal, which is shown in figure A, and the vertical lines I drawn here is the impulse, is the sampled values. Okay, so this is the amplitude. Now here I have used sampling frequency equals to 3f. Now this is actually, okay, this is the impulse train. Now what is an impulse train? Now this figure, that is, let it be figure C. Now this figure C shows that the signal sampled by using an impulse train. Actually, impulse train is a continuous signal consisting of a series of impulses which match the original signal at the sampling instance. Okay. Now, in figure B, where we have shown the frequency spectrum of the unsampled signal, you can see that it is composed, the unsampled signal, it is composed only of frequency component between 0 and, let it be 0.35 of fs, as because it is fs and it is 0.5 fs, and this frequency spectrum is completed before 0.5 fs. So let it be let takes the value as 0.35 fs. Okay, so here the frequency of the unsampled signal lies between 0 and 0.35 fs, where fs is the sampling frequency. Now the sampled signal is in time domain is shown in figure C, the sampled signal. Now if you, and its frequency, let's draw the frequency spectrum. Let's draw the frequency spectrum, and this is 0.5, this is fs, this is twice fs, this is thrice fs, and so on. So if it is that 0.35, so after so this is the way actually, that if we closely observe this frequency spectrum shown in figure D, what we can conclude, that we have find this frequency spectrum is the duplication of the spectrum of original signal. So this is the original signal which is shown in figure B. It is the frequency spectrum of the original signal, and I have sampled the frequency. It is actually lies in between 0 to 0.35 fs, and if fs the sampling rate, then actually this is the frequency spectrum of the sampled signal. So we find this frequency spectrum is the duplication of the spectrum of original signal, and each multiple of the sampling frequency, that is fs, twice fs, thrice fs, fourth fs, etc., has received a copy to the left and right of the original frequency spectrum. Now the right copy is called the upper sideband. This is the right copy, and this one is the left copy. Now this right copy is known as the upper sideband, and this one, that is the left copy, is the lower sideband. Okay. Now, thus we see that sampling has generated new frequencies. Thus, sampling has generated new frequencies. Now, a question must arise that can we remove or recover the original signal from this? Yes, of course. We can uh, reconstruct, or we can remove, or we can recover the original signal from this frequency spectrum by using a simple low pass filter with a cutoff frequency fs by 2. So that is the way that we can reconsider, or we can rather reconstruct the original signal. Now, in the time domain, sampling is achieved by multiplying the original signal by an impulse train. What is shown in figure C, that is, the sampling is achieved by multiplying the original signal by an impulse train of unity amplitude. Now, when two time domain signals are multiplied, their frequency spectra are actually convolved. This results in the original spectrum being duplicated to the location of each impulse in the impulse train. So, viewing the original signal as composed of both positive and negative frequencies accounts for this upper sideband and lower sideband frequency. So, this is actually generating some redundancy in the frequency spectrum. Okay. Now let's consider, so here actually what I have drawn, or what I have shown, that the original signal is limits to a frequency of 0.35 fs, and I have sampled this frequency, or I have sampled this signal around fs. So this is quite greater than the sampling rate as shown, or as discussed, or as mentioned in the Nyquist frequency. Okay. Now let's take a case for undersampling result. So if we undersampled the signal, so let's move on to figure E. This is our figure D. Now let's move on to figure E. Okay. So in time domain, again I am drawing the time domain picture. So this is the, I'm using these dots. Okay. Now, as I am talking about the sampling frequency, let's so this is the impulse. This is the impulse train. Impulse train. And here the sampling, here the sampling frequency is 1.5 fs, or 1.5 of, rather 1.5 of f. So the maximum frequency is f, and I have sampled it 1.5 f. So that is less than the sampling rate of fs, as because fs, that is the sampling frequency, according to Nyquist theorem, it should be twice of f. So this is undersampling case. Now if we draw the frequency domain, if we draw the frequency domain of this undersampling case, let it be figure F. So this is our Fs, So if this is Fs, this is twice Fs, let it be thrice Fs, and so on. What we can find that here and so on. So this is the case. This is the case. Now here what happens? Here some overlapping of the lower sideband and the upper sideband occurs. Here overlapping of the upper sideband and the lower sideband occurs. Now the analog signal, now this figure shows, figure F shows that the duplicated portion of spectrum overlap each other. These are the positions in which the lower sideband and the upper sideband overlaps with each other, and actually they overlap each other and invading the other's territory. Now, since there is no way to separate these overlapping frequencies, so the original signal will be lost or it cannot be reconstructed, as because the lower sideband and the upper sideband are overlapped with each other, and as a result you cannot, or there is no way to remove this overlapping, or there is no way to reconstruct these signals. So that is the error. Now this overlap occurs when the analog signal contains frequencies greater than 1/2 of the sampling rate. Actually, what we have talking about, or what we have done here, we actually sampled the frequency in 1.5 F. So we have actually undersampled the signal. So in undersampling case, in a brief or in one liner, what we can talk about that whenever you undersampled any signal, then the upper sideband in frequency spectrum, obviously in frequency spectrum, the signal or the upper sideband and the lower sideband of the signal overlap with each other, and thus it cannot be separated, or you cannot effectively remove or reconstruct the original signal, as because the informations from the upper sideband and from the lower sideband are mixed with each other or overlap with each other. Now this is the result what we are talking about, and this is known as aliasing. Aliasing is the effect, and aliasing occurs whenever, so this is the case of aliasing. This is the case of aliasing. So aliasing occurs whenever the sampling frequency is less than the prescribed sampling frequency, that is whenever you are undersampled, you are going to undersample the frequency, then only aliasing occurs. Okay, is it clear why aliasing occurs? In curve E, in curve E it is, Ipshita, in curve E it is amplitude versus time. It is amplitude versus time. Yes, Shubhajit rightly pointed out that it is amplitude versus time. Is there any question? Any doubts? So in this class, we have already talked about the sampling theorem. I've talked about the sampling frequency, about Nyquist frequency, Nyquist rate, and lastly, the aliasing effect or the occurrence of aliasing effect. Now let's move on to further, that is, let's move on to so we have already discussed about, or what we have talked about, that an analog signal, now an analog signal is completely, or according to sampling theorem, we have sampled the original analog signal. So now we have in our hand some discrete values of a signal, and let's discuss about a topic, that is PAM, pulse amplitude modulation. Pulse amplitude modulation. So now the topic is pulse amplitude modulation. Now it is actually the simplest form of pulse modulation. It is the simplest form of pulse modulation, and in this modulation the signal is sampled at regular intervals. So if this is the signal, then the pulse amplitude modulation, so after sampling the frequency, say we have sampled this frequency in this way, maintaining the Nyquist frequency. So if these are the values, then it may happen that these are the values. So in this way, these are the discrete values. So in figure A, an original signal is drawn, and in figure B, it is the double polarity PAM, double polarity, as because here the sampled values, as we get by applying the sampling theorem, I have drawn exactly the values. In the positive half cycle part, or in the positive part, when we are having the positive values, so these are the positive half cycle parts, these are the positive values, and for the negative half cycle the sample values are here. So this is known as the double polarity PAM, or we can draw this signal in single polarity form also. How can we draw in single polarity form? If the values, let the values are, say the maximum values is plus 5 volt and the minimum value is minus 5 volts, so that is the maximum value and the minimum value, let it be 0. Now if we want to draw a single polarity PAM, what we have to do, we have to add a positive value with the negative part, so that these negative values are converted into a positive one. So let us consider that we are adding 5 volts with each and every values. So that means if it is minus 1 plus 5 becomes plus 4 volt. If it is minus 2 volt of amplitude, minus 2 volt plus 5 volt means 3 volts plus 3 volts. This one is minus 5 volts, so minus 5 volt plus 5 volt means 0, and so on. Again, in the positive half part, you have to, or don't forget to add these plus 5 volt values to the positive part. So we are actually converting the entire values in one single side, or this is known as the single polarity PAM. So if in a single polarity PAM, if plus 5 volts is added to these sampled values, then if this peak positive value of plus 5 volt will be converted into 10 volts, so the entire signal should be taken as, say, every values is added up with plus 5 volts. That means the amplitude of the signal is added up with plus 5. Then the negative values should take in the positive range. So this is minus 1, it will be plus 4, minus 2 will be plus 3, minus 5 will be, say, 0, minus 4, that is plus 1, and so on. So this way, or this figure shows us a single polarity PAM. Single polarity. So this is a double polarity PAM. Double polarity PAM, and this is a single polarity PAM. Now here you may notice that every time whenever I have sampled the values, whenever I draw it here, I find the values, or I draw the values, not a single spike, but a value itself. It is a wide shape fringes here. Now, because whenever an original signal or an analog signal is sampled, say, since this is a continuous signal, so at 5 seconds I have sampled fast, or the sampled interval is 5 seconds. Okay, so at 5 seconds I found the value of the analog signal is 1 volt, but whatever may be the minimum value or the time interval, now just at 5 seconds you find the value as 2 volts, but it will continue, as because the information signal or the analog signal is go on increasing. So you may find that at a very short interval of time the value exactly changes from 2 volts to, say, 2.1 volts. Okay, so here there are two ways of sampling, or to get the values from the original signal, that is sampling values. Now these sampled values can be found in two ways. One is the sample and hold circuit. Now what is the sample and hold? Sample and hold means initially whenever the sampling occurs, that is at 5 seconds, if the value of the original signal is found to be 2 volts, then taking the value 2 volt constant, you are sampled it. So this way, this is a flat sampling. This is a flat sampling, that is sample and hold. So when the sampling occurs, the value found at that instant of time, it holds the value. So whether the information or whether the original signal changes its value, okay, whether the original signal changes its value, it we don't bother here. This is known as the sample and hold circuit or the sample and hold. So that's the way we get the flat top sampling. Okay, you may find that this may occurs that whenever the value is sampled, as because it may take the values as this, it may take the values as this, as because whenever you sampled at 5 seconds the value is 2 volt, and at 5.01 second the value changes to 2.1 volts. So here also this type of sampling you can find that this type of sampling also occurs, but this is the easiest case, this is the simpler case, that is we have assumed that the values remain constant, or these are the sample and hold values, where we have found that flat top sampling is possible. Now let's move on to another topic, that is the pulse code modulation. It is also an important topic. So this is what we have discussed again, that is the flat top sampling. Okay, now let's move on to another important topic in pulse modulation, that is the pulse code modulation. So here again I am talking, or I am starting the discussion from having some sampling values. So again the first step is, whenever you have found an original signal or an analog signal, firstly you have to convert it into digital one, that is you already arrived or already obtained the digital values. Fine. So we have obtained these values. Let's discuss this pulse code modulation from this figure. So these are the values which I have obtained after sampling the original analog signal. Now this original analog signal, or I can draw a clear picture. So the first step of PCM, the first step of, this is a value, then this one another, then this is another value, this one is another one, say this is another. So this is a dual polarity PAM, what I have discussed just now. So this is the information which I have gathered after applying the sampling frequency. Now, so the result of sampling is a series of pulses. So these are the series, this is the series of pulses with amplitude varies between between maximum and the minimum values or minimum amplitudes of the signal. Let it again +5, and this is -5 volts. So the difference, that is the values lying between +5 minus of 5 volts. So the value is Vmax, if Vmax is +5 volts, if Vmax is +5 volts, that is the peak, and if Vmin is -5 volts, then the value is Vmax minus of Vmin, that is 10 volts. Okay. Now in pulse code modulation, you have to, or we have to divide these entire values into number of zones or levels. Now these zones having height delta, and that delta is V max minus V mean divided by number of levels, that is known as L, or number of zones. Okay, now let us consider that we have decided to have 8 levels. So 5, 5, 10. Let it be 5 levels. Let L equals to 5 levels for 5 zones. Okay. So what will happen, that if 5 levels are drawn, then each height of the zone, that is delta, is 5 minus of minus 5, that is 10, divided by 5, that is the zone height should be 2 volts. The zone height is going to be 2 volts. So let's divide these values into 5 different levels having height of 2 volts. So let this is 1 level, 2, 4. So this is level number 0. This is level number 1. This is level number 2. This is level number 3. This is level number 4. Sorry. So no, I have to find these values a slide bigger, or I can't accommodate. So let these values are separated a bit. So let it be level 1. Let it be level 2. Let it be level 3, and let it be level 4. So these are 5 different levels. The figure is quite untidy, sorry. So actually what I have done, initially after getting the sampling values, from the analog signal, these are the sampled values. These are the sampled values. After that, I consider that these entire values, that is 10 volts here, this entire values is divided into some different levels. Now if these levels are 5, here I have taken 5 as because the difference of values is 10 volts, so I have taken 5. Now if the values are 5, then each height of each level is 2 volts. Now after that I am divided this entire range of values into 5 different zones. Okay, now then we have to consider that these different values resides or situated in which zone. For example, let us take this first value. So the first value lies in the fourth zone. This is 1, 2, 3, 4. So this is the fourth zone where the first value lies. After that, the second value. Now here you may consider that the second value also lies in the fourth zone. Okay. The peak is in the fifth zone. Okay. Later on, this value is also in the fourth zone. So in fourth zone, we found value number 1, value number 2, or rather value number 3. So these are the three values already positioned in the fourth zone. Later on, this value, it is actually in the second zone. This one is in the first zone. This one is also in the first zone. So these are the values in the first zone, and these are the values in the second zone. Okay, so here, now this is the process. It is known as quantization. I have quantized. I have made these values in different levels or in different regions, in different zones, and this is known as quantization of a signal. Now, in this way, when I divide the entire zone into 5 different levels, now these sampled values have positioned themselves in the same zone, or there are repetition of zones. Now, so you can say that, you can conclude that, so these three values, though these three values are different in amplitude, but after quantization you have find that these three different values actually position themselves in the same zone. This is the error. This is an error, and it is known as quantization error. So quantization error. Now, if you want to remove this quantization error, again considering these values, now these two values actually resides in the second zone. But again you find that these values are quite different from each other. Again, these two values quite differing with each other in amplitude, but they resides or they position in the same level. So this is called, what we have told, that this is an error and it is due to quantization. Now, again a question arises that how to remove this quantization error. Simple answer is this: you have to increase your number of levels. Let us, for an example, if you find, or if you divide this entire zone into 8 levels, just go on increasing the number of levels. If you go on increasing these levels, then the height of the level should also be reduced, and then 10 volts divided by 8, that means each of the level is of height 1.22 volts, 1.25 volts. Okay, so here then you can find that there are some cases here, whenever different values are residing in the same zone, but after dividing these into a number of levels greater than 5, you can find that these values different in amplitude, they are positioned themselves into different levels. So that's way we can remove the quantization error. But then why I have considered number of levels smaller? As because if you go on increasing the number of levels, actually what will happen, that the number of codes formed is quite greater. Okay, now if level number is 8, the code will be in 3 bits. Okay, since 2 to the power 3 equals to 8, as we are heading towards pulse code modulation. So we are going to generate a code for each and individual values. So if the levels are 8, then you have to consider 8 different values starting from 000 to 111. There are 8 levels, as you know, 8 values, 8 definite values. If one considers that no, I have to divide this entire zone into 16 different levels. Now, if you consider that you are going to divide this entire zone into 16 levels, that means this height or the zone of the height again reduced 10 divided by 16. So it will be very smaller in height, and thereafter you can divide or you can differentiate each and every individual values into individual zones. That is fine. But remember, whenever you are considering the number of zones into 16, that means you have to consider 4 bits at a time, as because 2 to the power 4 equals to 16. Now, two system two system engineer generated two different pulse code modulation system. One system engineer considered 8 different values, so he has to transmit 3 binary bits at once for each value, and the other one who have considered 16 different levels, he has to transmit 4 binary codes at a time for an individual value. So as you can know that transmitting 4 bits at a time is quite not commercially viable, as because transmitting 3 bits at a time is required less bandwidth. So as if you considering the cost effectiveness of the program, then actually considering 16 different levels or 16 zones is a quite costly affair. Okay, so in theoretically we must consider these levels as large or as big as number increases, the quantization error decreases. But remember, after decreasing the quantization error, you may appear at a stage that your transmission cost is very much greater. So that should be remembered in mind. Okay, so in this particular lecture, in this session, what I have discussed initially the sampling theorem, the Nyquist frequency, the Nyquist rate. After that, I move on to pulse amplitude modulation, in which I have discussed single polarity, dual polarity PAM. I have discussed the flat top sampling, and after that, I move on to pulse code modulation, in which I have discussed the quantization error, and how to remove this quantization error. Okay, so goodbye.